Greetings all present. Thank you for being here. My name is Serhiy Delhopolov, and together with my co-author Tatiana Honcharenko from the Kyiv National University of Construction and Architecture, I'm presenting our work, MACE, a modular adaptive code engine. In the next 15 minutes, I will tell you a simple story, how we built a code generation system that is at the same time faster and more correct than its base model, and how we did it on a single consumer-grade GPU. If you read the headlines, code-specialized language models look almost sold. Qwen 2.5, Coder, GPT, Claude all report pass rates above 90% on standard benchmarks. And yet anyone who has tried these models on real projects knows the truth. Benchmarks say 90%, real projects say otherwise. We see three persistent shortcomings. First, there is no specialization. The same parameters that generate a one-line CSS rule are used to generate a recursive descent parser, and the model has no notion of language, task type, or domain. Second, there is no project context, repository structure, abstract syntax trees, API contracts, all invisible to the model. Generation happens in a vacuum. The model has no idea your project already has a function called parse user input, so it happily writes a new one with a slightly different name and a slightly different bug. And third, there is no verification. Generation code can contain functional errors, security vulnerabilities, or style violations with no closed loop to detect or correct them. Each of these has a partial solution in the literature, but no existing system brings them together. This is the gap MACE fills. MACE is built on three contributions that work together as one architecture. The first is context-aware LoRA expert routing. A small learning network looks at the request and decides which domain-specialized adapters to activate, not based on raw tokens, but on high-level semantic vectors that describe the task. The second is a hierarchical three-level retrieval-augmented generation system. We retrieve context at three different scales: global documents, documentation, project-level structure, and local file the developer is editing. The third is a multi-signal verification loop. Every piece of generated code is checked along three orthogonal dimensions: execution, security, and style. And if anything fails, the system regenerates with structured feedback. Importantly, the base model weights are never touched. Every adaptation is parameter efficient and ephemeral. MACE is a 5-stage pipeline. Think of it's an assembly line for code. The input is a natural language request. For example, write a function that returns the longest increasing subsequence in O of n log n time. And stage 1, analyze. The context analyzer reads the request and produces a semantic vector. Stage 2, routes. The vector is fed into a learned router that selects which LoRA experts to activate. And stage 3, retrieve. The hierarchical RAG system gathers relevant context from three levels. Stage 4, build. A prompt is assembled from the retrieved context and the routing decisions. And the last stage 5, generate and verify. The base model, augmented with the composed expert adapter, generates code, and the verification loop checks it before it is returned. So let's spend a few minutes on the three most important design decisions. Traditional mixture of expert architecture wrote on token level representations, and this works, but it is opaque. You cannot easily explain why a particular expert was chosen. So we took a different approach. The MACE roads operates on a task level semantic vector, 26 dimensions derived from interpretable analysis, a one-hot encoding of the language, the task type, a complexity score, the domain, and the flag for whether code is already present. This vector is projected into embedding space and pastes through a two-layer MLP. The result is a probability distribution over the experts. We pick the top two and renormalize. And to prevent expert collapse, a no failure mode where the road always picks the same one or two experts, we add an auxiliary load balancing loss so that keeps every expert in the game. And here is the key insight. Once the experts are selected, their LoRA matrices are merged through a simple weighted linear combination. And the composition is ephemeral. The base weights are never modified. We can recompute the merge for every new request in real time, and something monolithic fine-tuned models and conventional mixture of experts architectures cannot do. The second contribution is hierarchical retrieval. Existing RAG systems for code typically operate at a single level, a flat index of documentation snippets or code fragments, and we argue this is wrong, because different kinds of context have different shapes. So we use three levels. Level 1 is global, external documentations, API references, community knowledge, and indexed in ChromaDB with code-specialized embeddings. Level 2 is project, and this is where it gets interesting. Instead of arbitrary fixed size chunks, we use tree-setter to parse the AST of every Python, JavaScript, or TypeScript file in the repository. And we extract complete functions and classes, semantically meaningful units. We also produce a repository map of every file and its top-level symbols. This gives the model structural awareness of the code base. And level 3 is local. The file's development is currently editing. We just deterministically extract the preceding code. The following code, the imports, the enclosing scope, and the local variables, plain windowed extractions, fast and exact. So we then deduplicate across levels and assemble the final context with a clear priority order. Local bets projects, project bets global. Proximity context is almost always the most relevant. The third contribution is the verification loop. Even the best model produces flawed code sometimes, so we check it. We run 3 checks in parallel. Execution testing with WAIS 0.5 runs the generated code inside a Docker sandbox. Security analysis with WAIS 0.3 runs Bandit. If it finds anything high or critical, the code is blocked. And style checking with WAIS 0.2 runs rough. This one is advisory. And the 3 signals combines into a composite score. If the score crosses the thresholds, we accept. If not, we regenerate with structured feedback, error messages, security findings, linter output, append it to the original prompt, and we allow up to the 3 iterations. This gives the user a turnable trade-off. More iterations means higher correctness, but also higher latency. And now let us talk about how we built and trained an experts. We picked Python as the first domain. We created a dataset of 12,450 examples, combining code alpaca, 20 20k with eval instruct code, 80k filtered for Python, and enriched with algorithmic and class-based patterns. And next, we trained for 3 epochs, so the whole process took 7.2 hours on a single NVIDIA RTX 4060 Super with 16 gigabytes of RAM, and the LoRa adapter has only 1.05% of trainable parameters relative to the base model. Those dropped from 2.19 to 0.35, and token accuracy reached 89.4%. The point I want to take away is mindful expert specialization no longer requires enterprise infrastructure. A graduate student with a good consumer GPU can train one of these adapters over a long weekend. To evaluate the result, we built a benchmark of 25 carefully designed coding problems, plus a 50 problem subset of human eval for external validation. The problems span 3 difficulty tiers: easy, medium, and hard, and 5 categories: algorithm, data structure, math, Pythonic patterns, and string processing. Correctness is strict pass-fail. Generation times is measured end-to-end, and we compare 2 configurations. Configuration A is a base Qwen 2.5 coder, 7 billion parameter with 4-bit quantization, and configuration B is the same base model with our Python LoRa expert loaded. Same model, same hardware, same inference parameter, only the adapter changes. So what happens? The base model achieved an overall pass rate of 84%, and the LoRa enhanced variant reached 96%. That is a 12 percentage point improvement consistent across all 3 difficulty tiers. On easy problems, 88 to 100, on medium, 90 to 100, and on hard problems, 71 to 86. A 15-point jump. To check this is not a quirk of our created benchmarks, we also ran a 50 problem subset of human eval. The pass at 1 rate rose from 86 to 92%, confirming that the improvement generalizes. The single LoRa failure was the expression evaluator problem requiring a complete recursive descent parser, but notice the LoRa expert solved several problems the base model could not. For example, including frequency-based sorting, balanced binary search tree verification, and the order n log n longest increasing subsequence. So, and now here is where the story gets really interesting. There is a common assumption is in machine learning: when you fine-tuning for accuracy, you pay for it in speed. In our case, the assumption does not hold. The LoRa expert is pulse more correct and faster. The overall speed up is 35%. Average generation time drops from 14.8 seconds to 9.6 seconds. On hard problems, 43% faster. Why is the LoRa expert faster? Our interpretation is this: the base model, when faced with an unfamiliar patterns, generates exploratory tokens. Its resistance, the fine-tuned expert has internalized more direct solution strategies. It commits, it produces fewer tokens, and they are more focused. So the trade-off is not correctness versus speed. It's untrained generality versus trained decisiveness. And the per category breakdown tell us where to focus future training efforts. The biggest gains are in algorithms, 80 to 100%, and in data structure, 60 to 80%. These are exactly the categories where we deliberate enriched the training data with class-based and traceful example. Math, Pythonic patterns, and string processing are at parity. Both configurations score 100%. These categories are well served by general purpose instructions, data, with no headroom left. And the lesson: targeted training works. If you want better performance on a specific category, you need to invest in curating data for that category. And let me summarize. We have shown that a single Python LoRA expert trained on a consumer GPU can seamlessly improve correctness by 12 percentage points and reduce latency by 35% without modifying the base model, and the verification loop closes the remaining gap. And we did this with only 1.05% of trainable parameters. So what comes next? We want to build an expert ecosystems, adapters for data science, security, web development, each trained independently, each composable. And we want to enable end-to-end router training, where routing decisions are themselves shaped by verification feedback. And we want to evaluate the hierarchical RAG component on repository-grounded benchmarks like CVE bench, where its structural awareness can really shine. And the full framework is realized as a Python package with a CLI and REST API ready to use, adaptive specialization on a consumer GPU. That is what MACE makes possible. Thank you for your attention. I will be very happy to answer your question.